Welcome back. I'm excited because today I get to bring together some of the many ideas we've been using. This is going to go under the name of a topos, an elementary topos to be specific. This is a name given by Alexander Grothendieck to a collection of properties that many types of data and logic have together, and it captures much of what we need in set theory. Remember, set theory was our get-out-of-jail card when we had too many contexts overlapping, and it made for contradictory statements in logic. So, by making sets, we narrowed our opportunities to say that these sentences apply to this context and another context. We thought about this as colored sheets of paper inside of a multicolored book, or you might think of chapters inside of a larger book. Once we think of gathering data between contexts, we'll need to transfer data from one context to another using functions. It's sensitive to some of the ground rules of the particular logic. If we're very constructive and we need to make programs, we'll be thinking much like intuitionistic or linear logics and quantitative logics in general. If we're thinking classically to model our real-life sciences, we'll think about true and false and get rid of all the evidence. If we're thinking about dealing with practical data where there's noise and other issues, we might deal with modalities, pair consistencies, and other types of ways to handle probabilities. What brings them together is the ability to model the flowcharts of the information between these different sets. For example, when we have a pair of objects, we can often form a uniform pair single object. We model that in our diagram language by saying 2 points lead to a third point. Then we add in the storyline of introduction and elimination rules to match them. In this model, we're creating a cone. So we look at the maps coming out of the data type we just created, the pair type. These are elimination rules. They're taking data away from our pairs, back to the original A and B. Then we try to match them up with what anyone else could have done so that our program is universal. And we consider our program to be the best if, in fact, it can take in whatever new lessons C had as part of its own. With this type of diagram, we're able to describe a Cartesian product. As a technical note, the function that introduces C to A over B is always understood to be uniquely defined. We'll get into specifics about quantifiers in a future lecture. For now, just assume there's only one of them. Here's what exponentials provide us.
The role of the exponential is to allow us to create programs that can combine fixed data, such as the charts of nutrition, with new incoming data, such as recipes, to create nutrition labels. In this way, we don't have to create a separate program for all new data. Instead, we use two types of data, one such as a chart to reprogram a new function, and another one such as a recipe to apply that new chart on new data. The result is, with minimal reprogramming, we get a function factory. This is known in type theory as the exponential.
We start with any two data types A to B. From that, we're able to construct an evaluation map. This evaluation function is meant to play the role of having genuine functions from A to B, without paying the cost computationally of somehow storing all such functions. So, for example, we could have had nutrition charts and an evolved program to convert charts into nutrition. Once we have this evaluation function, we want to make sure that we give ourselves as a data type the control to know it actually will produce all the necessary functions. To do that, we compare it to some other competitors. Suppose that someone comes up with an alternative set of choices to reproduce some of the functions from A to B. They create their own version of an evaluation map. Ours will be universal if it can reproduce what theirs can do. What we see is that we created an introduction rule for our B to the A, our exponential. Anybody's alternative evaluation map has to be able to turn into one of our objects that we could evaluate with our algorithm. This is the standard story of universal programs. We don't actually have to anticipate the future and know every engineering trick that could ever happen. We simply need to be able to adapt with the changes. If a new change comes along, we want to be able to convert all the data that already works on our program to use these advantages without much overhead. This introduction rule guarantees that. These two pictures together capture an important piece of mathematics known as the lambda calculus. Notice these two pictures reinforce each other. We need Cartesian products and we need functions at the same time. We couldn't form the Cartesian product pictures without the arrows, and we couldn't form the exponentials without the Cartesian product. They are a symbiotic relationship, and they're related by one master theorem, which we saw when we did proofs with sequence. This relationship in the middle is the observation that we can think of pairs mapping into one data type, but think of a single data type mapping into an exponential. It's so important that I'm going to call it the fundamental theorem of lambda calculus. It's a play on the fundamental theorem of calculus, but you might find this in the literature known as the theorem of simple type theory or Cartesian closed categories. By whatever name, this property is an essential foundation for any good programming system. It lets us start to move between pairs of data and functions. It lets us reinterpret our data in multiple ways. It lets us plan for the future by letting us work universally. It's also the minimal amount of logic necessary for almost anything. It requires us only to have implication and conjunction, that is the and. From these two properties alone, we go quite a distance. But wait, there's more. Beyond Cartesian closed categories, we also might want to talk about sub-objects and subsets. And for that, we need two more constructions, limits and subset classifiers. Cartesian products are great. They take two data types and they form a new data type. But what if we need a data type that's aware of some of the behavior, some of the flow of the information? For that, we need to match up diagrams. We've already seen how this can be done with cones and cocones. I'll remind you of the architecture. We start out with a diagram that already commutes. That is, any two paths to the same place give us an equation. What we now want to do is build a master data type that captures that entire diagram all at once, similar to how the Cartesian pairs took two data types and made one uniform data type. The only requirement now is that as we create that unified type, we don't want to change what commutes. We still want to maintain all the equations that are already true in this downstairs picture. There are two ways to go. We can either create a data type that's a master one on top that sends its data down to the one we have, or that takes the data we have and combines it into one. These will be generally two different types of data. This is why we have both cones and cocones. What we're adding today is purely the existence of a final and best answer. In general, those don't have to exist. So I'll draw the picture for the cone. If you need to dualize it, watch our video on cones and cocones. I'll draw a single dot above the plane of all the data whose flow we're trying to master. We have this flow chart of information already set in stone. We don't want to disrupt that. Our next step is to add arrows that go from our diagram to the dot or the other way around. The orientation is what distinguishes it as a cone or a cocone. In this series, I've assumed that all my arrows will start from the top and go down, so that will make this one a cone. The only requirement of this cone is that all of these be morphisms and that any two paths to the same point agree, they're equal, they commute. So, we can often remove some of the edges because we could reconstruct them from these equations, but I'll leave all of them in for today. The next stage is to guarantee this was a universal solution. To be a universal solution, we wanted to guarantee that anybody else who built a similar cone would always be able to take their data and transform it into ours, or vice versa. The configuration depends purely on the orientation of the arrows. Since we're drawing cones, that means that we'll consider somebody else building an even more sophisticated, larger cone, and that theirs can at least be mapped back to our more primitive one. That will make ours universal in the minimal sense. Our competitor adds their own cone, going wherever they wish to map, but maintaining the commutativity of this diagram. The last step of this is that there should be a path that introduces their data into ours. At this point, our cone can transfer anyone else's information into the representation we've created. Our program is guaranteed to last into the future by that virtue. The entire point of this lesson is to focus on whether such a point even exists. When we have data structures that are robust enough that they guarantee the existence of such a cone, then we're prepared to say that this category of data has limits. But I've left room for one key word. There's a nuance here. Sometimes this data depends very much on an iterative process, the ability to count, the ability to store data in a finite amount of time. Other times, we have such powerful data types that we could actually add any number, even infinite numbers of data. That would only work conceptually, not computationally, but the freedom to build such a data type is stronger than strictly saying that we can build it for finite types. So, there are two types of limits we might consider here. There are finite limits and infinite ones. It's a custom these days to tell our audience whether we're dealing with finite or infinite limits. While computer programs will only ever deal with something finite, often the models we're talking about in classical and data science problems will concern infinite limits as well. And it's important to be able to use these two different languages. You can start to see the emergence of a calculus of sorts, a way of calculating, only what we're calculating with here are data types. The idea of a limit will resurface when we go back to classical Newtonian calculations. where we try to calculate where our numbers going, what progressions of decimal places are getting approximately closer to other numbers. It's all part of a family of many ways to do calculation. So while there are many ways to calculate, you should start to form an opinion that perhaps behind most calculations are some general principles. We try to build up some general operations on how to glue things together. And then we try to see which patterns emerge if we take those calculations into repeated steps. In this case, the repetition is, what if we create one cone, a way to combine all the data in some flowchart into one master data type, such that if anyone else built a different representation, we could always benefit from their approach because they could convert theirs into ours. So we want a universal representation. If such a universal representation lives in our systems, then we say that our system has limits and that it's complete. Notice we could do the exact same thing with cocones, taking all our data and compressing it to introduce a new data type, such that if anyone else could introduce similar data type, we could convert ours into theirs. That conversion would be universal. If that process existed, we would say that this has limits as well. But to remind ourselves that they're involving cocones, we'll go ahead and call them co-limits. And likewise, if we include the infinite variety, we'll say it is co-complete. It may seem that having arbitrary limits and co-limits is an incredibly powerful assumption. After all, how many different flowcharts could you possibly draw? But the point is, we have all the necessary ingredients to go in that direction. Let me show you how. Suppose that I wanted to take the limit of a diagram like this. This sits at the bottom, I create a cone on top, and I want elimination rules back to this data, but I want it to be universal. What chance do I have of making something when it gets very complicated? The answer is to break it down into small parts. Take, for example, these two isolated points. If we ignore the rest of the diagram, this should be a familiar diagram for us now. This would be a pair of objects, and we create the Cartesian pair. That we know how to make universally, and we've now turned 2 points into one. Now concentrating on this and the rest of this picture might be less intimidating. Over here we might notice a few shortcuts as well. Notice that here the arrows have to commute. They're pointing in the same direction. And because we preserve the commutativity of our diagrams, we only have to worry about the endpoints. The composition comes as a consequence. So we really only need to worry about these two arrows coming together. Once we create that diagram, we can then compose it with these outer parts to lift the rest of it. But if we look at just two arrows, we've seen that before. That was a pullback diagram, and we learned how to solve those too. There's one other thing that we will need, which is called the terminal object. With the terminal object, the key idea was that there was always a way to get to one single point. It turns out that by cutting up our diagram, our flowchart, into parts of disjoint pairs, pullback diagrams, and terminal objects, we can recapture all the structures that could ever occur as a bunch of intermediate smaller structures that we progressively build up until we make one unified data type. That universal construction is our universal data type. This is why most programming languages have the ability to create data types that can model any complex system we could ever want. They are generally complete and co-complete. Of course, some of this story falls apart when we start to consider resources or the ability for data to come back in incoherent ways. Nevertheless, the idealized solution now exists. We can say that a programming language is complete and co-complete. It has its limits and its co-limits. It also still has our Cartesian pairs and our exponentials. The last ingredient was our subset classifier. These were our predicates and our chi functions. They told us what it meant to have a proper subset. There we have it. What we've been exploring is a topos. It's an elementary way to model some of the most complex behaviors we see in the real world, from set theory to all the various degenerations in real classical data to the foundational stuff we need in computation. To pull this off, we needed a few basic primitives. We needed the ability to build ordered pairs, ordered triples, and beyond. Exponentials replaced the role of functions, giving us an evaluation function. Limits and co-limits said that we could slice up any flowchart into smaller pieces, creating a universal data type that could capture the unified behavior. That's exactly what a good model should be able to do. And subset classifier says that we can pick out of this flowchart the data that's relevant to our storyline. In almost every scientific situation, there's a set theory running around, a place in which facts are true within those individual sets, those individual smaller contexts. To relate these relationships together, we need a set theory, functions and relations between these sets. The minimal amount that we need to turn that computationally is a topos. These ingredients behind me each have interpretations in most modern programming languages. So in theory, we're ready to compute any complex model that a scientist might think of. We simply write their set theory down as a bunch of flowcharts, commutative diagrams that match up the individual smaller parts. Each data type is then mastered into one universal data type using this flowchart type constructions, these limits and colimits. Those are based in turn on exponentials and Cartesian products, the actual working gears that do the calculations. At the end, we clarify which subsets are relevant to our storyline, and now we're ready for a computation. To quote one of my former professors, Boris Botvinnik, this, in theory, is good enough for practice, which is good enough for theory, but not for practice. Until next time. That's how you take care of your chalkboard.